is looking at insights into electric vehicle battery life cycle analysis. My name's Gloria Esposito. I'll be chairing the session today, and I'm Head of Sustainability at Zemo Partnership. We have a great lineup of speakers this afternoon. I'm very pleased to have representatives from the lithium battery supply chain and experts in life cycle analysis, including the Advanced Propulsion Centre, Argonne National Laboratory, Minviro, Roskill and University of Warwick. And I'll give everybody a detailed introduction once they start their presentations. So just as a background to Zemo Partnership, we're a unique cross-sector collaboration of more than 200 organisations that are focused on accelerating road transport to zero emissions. We were actually created in 2003 and were formerly known as the Low Carbon Vehicle Partnership. We're joint funded by government and our members, and we have a real cross-cutting sector of different organisations, from automotive manufacturers, energy and renewable fuel suppliers, national and local government, the finance and leasing sector, and environmental organisations and academia as well. So in the terms of the work that Zemo team do, we work with our members to help deliver the UK's net zero policy ambitions. And really we focus on 4 key areas, and that's engagement. We bring together a diverse range of stakeholders to really act as an independent platform for debate and collaboration and information sharing like we're doing today. We have expertise in policy research and development, and we do a lot of work in emissions analysis, looking at different vehicle technologies, fuels, energy and infrastructure as well. We've got a variety of initiatives that we create and deliver, and those are primarily to overcome market barriers, both regarding the supply and the demand of low emission mobility. And finally, we do a great deal of work in terms of informing and shaping policy. We've been very successful since 2003 in influencing the car, bus, truck and renewable fuels policy landscape very successfully. Most recently, we've published a number of reports. For example, we've done some very interesting work looking at hydrogen vehicle well-to-wheel greenhouse gas and energy performance. We've also done work on market opportunities for renewable fuels in the heavy-duty vehicle sector. We've produced, low-emission vehicle and technology guides for fleet operators, and we run collaborations like the Electric Vehicle Energy Task Force and the Renewable Fuels Assurance Scheme, and all that information can be found on our website. So just to start off really, why is understanding life cycle impacts crucial for the journey for net zero? Well, the deployment of zero emission vehicle technologies and energy supply chains must avoid unintended environmental impacts. Whilst we focus primarily on reducing greenhouse gas emissions, the focus very much is on the tailpipe. We need to think about what's happening along the life cycle, whether that's vehicle production, whether it's the upstream primary energy, and at the end of life as well. But in order to achieve those deep cuts in greenhouse gas emissions, we do need to address the whole vehicle's life cycle, and as I've mentioned, look beyond the tailpipe. What's becoming more important is really understanding the performance of different technologies. And as you can see here on the right-hand side, battery electric vehicles, so this is an example as a medium-sized car, do perform much better on a life cycle basis compared to an incumbent diesel vehicle. As you can see, a large proportion of those life cycle emissions do actually arise from vehicle production, and about just over 50% of those are from battery manufacturing. As we move into the future and the grid decarbonises, those vehicle production emissions are going to become more influential, and lithium battery life cycle analysis will be crucial in terms of meeting decarbonisation. So I'd just like to stop there and introduce our first speaker. So I'd like to ask Jon Regnart to start presenting. Jon is the APC's Automotive Trend Specialist who has been with the company for 6 years, His role is to identify and communicate opportunities for UK in transitioning to net zero mobility systems. He is the co-author of the UK Automotive Council roadmaps, and he has published numerous reports on the opportunities and challenges of building electrified supply chains in the UK. So over to you, Jon.
Thanks, Gloria, for that really good introduction. So as Gloria said, my name is Jon Regnart. I'm from the Advanced Propulsion Centre. Very briefly, for those of you who aren't aware of what the Advanced Propulsion Centre do, we are a UK government funding agency that works very closely with the automotive industry to invest in late stage R&D and capital projects. And as Gloria said, part of my role is, I've heard it described as crystal ball gazing, where I try and look into the future of, be it batteries, motors, power electronics, and understand where the UK's got strengths, where there's opportunities to improve. And part of that is doing technology roadmaps and supply chain analysis. So the focus really today, what I wanted to try and do was, we're going to have many presentations on the very specifics of LCA and the impact batteries have. I just wanted to take a step back and understand what's going on the sort of product level on the automotive industry in terms of battery chemistry and how that has a knock-on effect on LCA. So how does that, so the chemistries, and then how does that affect supply and demand, which will then impact sort of LCA. And I'll go through the Automotive Council technology roadmaps and the electrical energy storage roadmap, and I'll pick out key sort of themes from the roadmap and sort of understand what innovation is happening in the industry to address some of those challenges, because the roadmaps, every single technology roadmap has a dedication to LCA. So first, I just wanted to give a quick whistle-stop tour of battery chemistry trends, because if you read the news, there's a new type of chemistry being invented every day. But I feel like the automotive industry has kind of converged around three broad classifications of battery chemistry. So on the one spectrum, we have entry level, low cost. We then have a middle sort of section, which is high volume performance. And then right on the other sort of performance end, we have high performance specialist applications. And if you look at Tesla's and VW's battery day, whilst they brand their different segments differently, it's effectively the same thing. So both VW and Tesla have sort of opted or want to opt for LFP in their entry level models. The middle sort of segment is the VW have opted for a manganese rich option in the future, whereas Tesla have stuck with a sort of combination of nickel and manganese. And then there's this sort of ultra high performance for the Tesla sort of Cybertruck and semis, and then for VW it is the equivalent of kind of the Porsches and Audis. So this kind of three segmentation is what we're seeing. That's the convergence. The divergence is the specific level solutions, and that makes kind of predicting future chemistries and the impacts on a life cycle analysis very hard, because this isn't a moving, this is a moving goal and it changes continuously. And I'm sure we'll hear that as a challenge in recycling as well. And just to further overlay, we've got the automotive kind of segmentation approach to battery chemistry choice, but there are also cross-cutting technology themes that will influence what gets chosen on a chemistry level. So topic of today is LCA considerations, and that's driving things like battery recycling, dry electrode manufacturing. You then have things around manufacturing improvements, because manufacturing improvements are sort of the often forgotten way of getting additional performance, and that drives kind of metal to electrode technologies. So it's some interesting stuff that Nano One are doing with one-pot processes for cathodes and pre-lithiation techniques for sort of pre-lithiating anodes, so you don't lose as much lithium in the first cycle. A big consideration of the last 6 months with the GM Bolt and the sort of some of the Kia recalls is safety. So a lot of work's been done on high voltage electrolytes and new current collectors. So that's another thing that drives different chemistry and different technology innovations. And then the supply chain vulnerability. We're likely to experience lithium, nickel shortages in the future. So that drives through sort of necessity, looking at alternate chemistries that are more abundant, and that drives a low cost. And I'll talk about that later. So what all this means basically is this slide that been produced by consultancy Romotion, basically sees a role for a lot of nickel-based chemistries in Europe You'll see there that there's NM and LNMO, which is the manganese rich. So we can see that's kind of coming in the mid 2020s, and that's probably to reflect what is likely to be a nickel shortage in that period. LFP currently predicted in Europe is quite small, but I wouldn't be surprised if that becomes a lot bigger, especially with the Model S announcement standard being LFP and a number of European OEMs wanting LFP. So that raises some interesting questions about European production and the life cycle impact of LFP as well, being on large lower than perhaps nickel-based chemistries. So what does this all mean for raw material demand and supply? Well, and why does it matter? Well, the International Energy Agency show that there's going to be an exponential rise in demand for things like nickel, cobalt, lithium, graphite, and other sort of elements that go into batteries. And there's a sort of sustainable development scenario, which is net zero compliant, and there's a stated policy scenario. And this is a very, very wide range. So what we did at the APC was like, okay, let's use our own sort of forecasting sort of models that we've got internally at the APC using a blend of different data sources. And what we kind of found was that using global xEV production data, we're a lot closer to the sustainable development scenario than we are to the stated policies scenario. So this rush for raw materials is going to create a problem, not in terms of economic problem, it's also going to create an environmental problem, because what we're seeing is a supply shortage, and that's going to hit in the next 3 to 5 years of these materials, not a geological scarcity, just a sort of economic scarcity in the sense of, oh, okay, well, it takes a lot longer to build a mine than it does a gigafactory. And at the moment as well, there's no incentive for some of the nickel miners to open mines, because they'd much prefer to sort of, supply into some of the steel networks, because at the moment the price isn't high enough to justify any investment. So they kind of like the fact that there could be a shortage. So what we would see in the midterm, or sort of the medium term, is that in a scrabble for kind of resources, at any cost, you may see, especially from sort of more developing nations, is that you may see resources that are perhaps not the most carbon friendly, and perhaps processes that are just trying to get the materials to meet demand rather than looking at it holistically. And that's kind of what this transition to high nickel chemistries kind of does. It may create kind of this panic to get the materials. I've kind of gone into what does this mean for LCA, but I'll continue. So I'm going to go into the roadmaps. I'm going to pick out key technology themes, but before I do, I just want to quickly do a 101 on roadmaps. So the APC, in conjunction with the Auto Council, have two types of roadmaps. We have product roadmaps that looks at the future of vehicle segments, so light duty vehicles, heavy goods and off-highway vehicles, and buses and coach. And then we have specific technology roadmaps, and they look at the future of the specific technologies that feed the product roadmaps. I'm just going to be looking at electrical energy storage because that's where batteries live, but these are all downloadable on the APC website, where we have detailed commentary and a set of industry challenges that sort of explain what the detailed R&D challenges are. So this is what the electrical energy storage cell materials and manufacturing roadmap looks like. Just quick explanation: on the left hand side, those grey categories are the broad categories of what you see in a lithium ion cell. What we'll be concentrating on is the bottom bit that says life cycle and end of life for cell materials. And the first thing I want to bring up is trying to reduce the CO2 in manufacturing processes. This is already biting OEMs and cell manufacturers quite hard. A lot of OEMs are already stipulating that they want carbon neutral or cells made from renewable energy already, as part of sort of a differentiator from Chinese-based cell manufacturing. And kind of agnostic of whatever chemistry you will use, it is quite energy intensive in a gigafactory to make cells, irrespective of chemistry. So in terms of low hanging fruit and what you could tackle first relatively quickly, I feel that this is an area that you could go on. And just to sort of labour that point, VW's delivery promise is very much we want CO2 neutral production, including supply chains, and they highlight the fact that cathode production and the sub-supply chain of raw materials, and I'm sure a lot of people will go into the specific inventories of raw materials because nickel and cobalt's very high. But in terms of cell assembly, that is also quite a big energy consumer. And what you notice is, so from a paper from I think it's from Nature, is the majority of the energy when you're in the cell manufacturing is in the dry room, so maintaining the dry room, and then the drying and solvent recovery of electrodes. So it's over kind of 80% of the energy intensity, and that's a lot to do with the solvents that we use in coating electrodes and the fact that the environment that you need to be in needs to be very sort of non-humid and stuff. So things you can do on top of that as well. NMP is actually quite hazardous. It's quite a nasty chemical. It's toxic. So you need to vent it very safely. So if you move to dry electrodes, there's loads of benefits of doing it. You reduce cell assembly OPEX and CAPEX. You don't need to vent the solvent anymore, and it requires also very under European regulation. It's very admin intense to have a permit to use NMP. So a lot of companies are looking to reduce the energy footprint and to reduce kind of the OPEX and CAPEX costs to move to dry electrode manufacturing. So the most famous is Tesla using kind of ultracapacitor technology as part of their 4680 cells, but LG, VW, and there's other sort of institutions that are looking at commercializing dry electrode manufacturing in 2023, 2024 that will massively reduce the energy input in the gigafactories as a result of eliminating the dry-in process. Another thing that can improve LCA is moving from energy intense raw materials to more abundant and less energy intense materials. So the battery industry has a rich heritage of chopping and changing materials, albeit it's for energy density reasons. So the first Tesla was an LCO, which has had a lot of cobalt in. Then Nissan went to LMO, which was manganese lithium, which was a lot more abundant, but not as good energy density wise, which then precipitated the adoption of NCA and NMC to get the range up. But in the present day, we're facing the ethics of cobalt extraction, lithium shortages as well, and carbon taxes as well. And being as though nickel, cobalt, and some lithium hydroxide are the most energy intense processes, it kind of necessitates a move to perhaps other options to reduce the CO2 intensity of the materials, but also to reduce the risk of supply as well. So that's why things like sodium ion manganese rich LFP, 0% NCA and NMC chemistries look attractive. And it's kind of the point of this slide, it's all to play for. There's not one chemistry that the automotive industry is looking at to reduce not only the CO2 intensity of the raw material supply, but also kind of to shield itself from any price increases. And finally, I don't want to take away from sort of other people's presentations, but it would be remiss not to mention the fact that recycling as contribution to sort of a more sustainable sort of industry. So the point I want to impress is that a lot of the news looks at minimum levels of recycled content as kind of the thing that's interesting. Just want to impress the point that there's recycle efficiency and recovery rates, labelling requirements, and carbon footprint declarations. And that's part of kind of a very big timeline that the EU, for its battery directive, talks about. And so this is sort of the full kind of gambit of different things that the EU is looking at. But I don't want to talk about this too much because Stuart is going to tackle this in his presentation. So just to summarize, OEMs are converging around 3 categories of batteries, converging around them for different EV portfolios, but specific chemistries diverge between OEMs within those categories, as the VW and Tesla battery strategy shows, and Renault's and Ford's and everyone else's. The burgeoning demand for nickel and lithium and graphite embeds the CO2 in the battery supply chain, as the extraction and refining of these materials are the most energy intensive. Refined battery materials and electrode manufacturing processes tend to be the most energy intensive, and for the cell manufacturing, irrespective of what chemistry you need to manufacture the cell, so perhaps dry electrode manufacturing could drastically reduce energy consumption. Batteries like LFP, sodium manganese rich, that use more abundant materials can lower the cost and environmental impact. And again, recycling batteries can reduce reliance on the primary materials, which reduce the footprint, environmental footprint, and can lower the cost as well. So that's sort of a really whistle-stop tour on touching on some of the LCA from an automotive perspective. Thanks for listening. The emails and the the whole technology trend team just flashed up there. Appreciate any questions towards the end, and thanks for listening.
Thanks a lot, John. That was a fantastic introduction. So moving on now to look a little bit deeper at lithium battery life cycle analysis. I'm very pleased to bring Gerard Kelly to the fore. I'm very pleased that he's come from, well, not literally come, he's dialed in from Chicago this morning. So Gerard is a principal energy systems analyst in Argonne National Laboratory Systems Assessment Centre, where he conducts life cycle analysis and helps develop the GREET model. His recent research has focused on vehicle electrification and lightweighting. He received his PhD and MSc degrees in mechanical engineering from the University of Michigan. So over to you, Jared.
Thanks so much, Gloria. Much appreciation for the introduction that John just provided us. I thought it was really great, really interesting stuff. A lot of dovetailing with what I'm talking about, because we're all sort of circling the same space. So there's going to be some commonalities in the things that we discuss. With respect to the work that I'll be talking about, I'll be getting a little more into the details of lithium, in particular, where it comes from, how it's extracted, that sort of thing. But I will be zoomed out a little bit and talking about our analysis that we conduct on lithium-ion battery life cycle analysis at Argonne National Labs. So obviously the main motivator for this work is that the demand for lithium-ion batteries is going to be multi-sectoral. It's going to be broad in scope. So we're going to be seeing it not only from automotive sector, we're going to see it from stationary storage, we're going to see it from within the automotive sector, we're going to see it across both light and medium duty, and medium and heavy duty. And then we'll of course continue to see demands from the personal electronics and personal transport as well. So all of that to say that we're going to have a significant demand increase globally for batteries on a gigawatt hour basis. And this is further motivated by the transition that many of our countries have laid forth in terms of carbon reduction goals. So with that in mind, what I'll be talking about today is the use of Argonne's GREET model for life cycle analysis, the development of our lithium-ion battery life cycle analysis work, and then further our recent analysis looking at lithium LCA from brine and ore, and then I'll talk briefly about the effects of location on battery LCA, so where things are produced and how that affects the results. So as a bit of an introduction for those of you unfamiliar with the GREET model, and I understand that I'm speaking mostly to folks, I believe here, mostly to folks in the UK. The GREET model has been supported and developed through Argonne National Labs by support from the Department of Energy since 1995. Initial focus was on vehicles, primarily thinking about well-to-wheels, obviously, so that in doing that, we're considering all of the energy and emissions that are associated with the extraction and production of fuels and the delivery of those fuels to a vehicle. We've also extended in the past decade and more into what we call the GREET2 model, vehicle cycle modeling. So that's all of the materials that go into a vehicle. But we've also further expand into just technology. So we're not focused necessarily on vehicles specifically, but that's sort of the history of the tool. So we have extensive coverage in terms of the number of users, the location of those users, the industry and the government involvements. So as you can see here, I've shown some of the organizations that we work with in different capacities and sort of the locationality of where those individuals and organizations sit. In terms of battery LCA, the Argonne team has been working on this since, I want to say, about 2010, looking at the development of detailed LCAs for battery technologies. The work that we've done for the battery itself, right? It covers, the dashed outline is basically saying everything that's inside of the battery. So that's going to be the cathode active material, the anode, the binder, the electrode, BMS. And some of the information in here, some of the boxes are a little bit dated, but I've tried to update them a little bit. Obviously, if we're talking about the cathode active material, we're in the context of a lithium-ion battery, we're going to have lithium that's going to come from either a brine or an ore process. I'm showing here lithium carbonate. We can do lithium hydroxide. We have that too. And I'm showing here for a nickel, an NMC chemistry of varying, XYZ, so nickel-rich potential. So those are going to also require nickel, cobalt, manganese sulfates. Additionally, we'll have all the input materials that are necessary for the production of these different materials. We have the anodes, the binders, etc. In the background, we also have, the more basic materials, your aluminums, your steels, etc. All that comes together in an assembly process, right? And we've heard already from Jon about some of those challenges, and I'll talk about that as well a little bit. In this talk, I won't talk about the use phase. I won't talk about recycling. We have recycling capabilities. In fact, Argonne has a center called the Resell Center, funded by the Department of Energy, looking at battery recycling. And we have another standalone tool called the Everbat model, which allows us to do comparative analyses of virgin battery production versus recycling through pyrometallurgical, hydrometallurgical, direct, different recycling approaches. So it's a flexible, extensible tool. So as Jon was mentioning, when we talk about cell production, that's one of the main challenges in terms of one of the big energy consumers. And the challenge here is essentially that we've got the electrode production, cell stacking, current collection, all those stages, right? But these steps have to occur in a dry room, and that's to prevent the electrolyte salt from reacting with water. So the moisture content has to be below 100 ppmv. So that's really been an issue, and that's one of the reasons that we see some differences in some studies from a life cycle perspective. So these dry room conditions must be maintained regardless of total throughput. So I think many of you are probably aware of this kind of thing, and some of the early analyses from a life cycle perspective represents the challenge in sort of honing in on what is quote unquote correct. And so the energy demand for the cell production within the GREET model was updated in 2017, and that's based on primary data from a 2 gigawatt hour battery production line that was operating at 75% capacity. So the dry room operation and electrode drying, as we noted, those are the two most energy intensive processes in battery production. So ensuring that the throughput of the battery line is high allows you to ensure that you are going to amortize that energy over a larger number of batteries. So essentially, the energy consumption is going to scale with the volume of the production location, and the same dry room higher production is going to give you lower per kilowatt hour energy demand. So we're showing here the comparison of a couple different studies looking at their suggested megajoules per kilowatt hour. You can see that our most recent study was shown here. So for context, GREET is updated every year. So while this specific value is the same, we have newer versions of GREET where additional materials and things like that are updated and knowledge is expanded. Additionally, we've done quite a detailed analysis looking at all of these different NMC precursors. This is looking at, this is a little bit dated, so it's looking only at NMC 111, but essentially we can do the same thing for other chemistries. This is indicating the energy sort of profiles of these different materials and the type of energy. We're just separating them here into fuel and electricity. Obviously, these are broad categories, but I think one of the important things to recall is that, of course, electricity is maybe more easily decarbonized than quote unquote fuel. Not that some of these processes that use fuel couldn't be converted to an electrical based process. So this is just looking at the various materials and stages of production for the NMC 111 battery. We can see here that aluminum obviously is a driver. Cell production is a driver. You can see the drivers in different ways. Cell production is more reliant on quote unquote fuel, and aluminum is more reliant on electricity. Additionally, the NMC precursors and production stages combined are significant energy consumers. Now, what I'll talk about now is the recent efforts that we've been conducting at Argonne, so within the lithium-ion battery space. So we've recently published a paper on lithium from both brine and ore, considering production in Chile and Australia with processing in China. So both of those represent, relatively consistent with the practices today, and it's the basis for the data are for the brine, it's for primary data, and the ore is based on modeling data. And then I'll talk about regionality. So again, where these batteries are produced, how that affects the greenhouse gas burdens. We have the rest of the life cycle, but I'll only be talking about greenhouse gases today. And then as we go along within the GREET model, we are continually refining the battery energy and composition based on the latest BATPAC model. BATPAC is a detailed battery production and cost model developed at Argonne National Labs. And so that's where we get a lot of our information from. So many of you are probably familiar with these sort of generalized diagrams of production of lithium from either brine on the left or ore on the right. So with the brine extraction process, right, you're just pumping brine from a reservoir into drying ponds. These stages shown here are obvious simplifications. This is a process wherein you have potash as a byproduct. So you, of course, are going to have a multitude of different constituents within your brine. So you're going to have to precipitate those out and refine your drying process to come to the sort of end point where you've got a concentrated lithium brine. That's going to go to lithium carbonate and then lithium hydroxide production. Those are shown here. So within the process information that we received from our industrial partner SQM, we had process-based information for the drying ponds operation, and we had sort of facility level information for the carbonate and hydroxide production. So that's why I've kind of got this in a little bit of a black box, as you can see. So that's just showing that for this process, we have your energy, the water, the materials coming in for the total quantity of carbonate out, and similarly for the hydroxide. We also have did a modeling effort to look at production of lithium, spodumene concentrate from ore mining. So obviously there's several size reduction stages, flotation, et cetera, until you get to the spodumene concentrate. Then that's shipped over to China. And then we used a public report from Jiangxi their production of carbonate and hydroxide. Generalized production process for hydroxide is shown here. This is not necessarily what the Jiangxi Corporation is utilizing. This is actually from Ullman's Encyclopedia of Chemical Processes. So this is just a representation. But so we were able to leverage the information, again, energy and material input data, to identify the life cycle burdens. What I'm showing here are the results of this analysis. So we went all the way from lithium extraction from the earth to the production and utilization within a battery. What I've done, because that allows us to put them on a common footing, right? Comparing carbonate to hydroxide doesn't really make sense one-to-one. So we usually go to this kind of sort of a basis. However, in this talk, I wanted to just show the comparison of brine-based carbonate as shown here versus ore-based carbonate on the right. We can mostly ignore this. This is an LCA thing related to process approach and sort of allocation. So the focus would be on the left, the rightmost grouping of these brine bars within carbonate and hydroxide. And we can see that in both cases, the brine-based approach is significantly lower in greenhouse gas emissions. So that sort of information is now underpinning the model within GREET. So we have that available to users. We released our model publicly. Again, we do an annual release in early October, so that's publicly available. I'm also showing here a little bit of older research from, I guess this was actually published last year, but the work was done in 2019. This is just looking at the global regional production of NMC 111, considering like a best case scenario. So this is, we took all the information that we had, and to the extent available, converted processes to different locational characteristics, so electricity, et cetera, for sort of a best case scenario, a worst case scenario, and then what we have as our baseline, which is a bit of a US-centric approach, and then the dominant supply chain. So dominant supply chain is obviously highly related to Chinese production for many processes. You can see that the drivers here tend to be aluminum, which should not be surprising, right? Because aluminum is so electricity intensive. So from a greenhouse gas perspective, if you're getting your aluminum from the US and Europe, there are a lot of hydros involved, so it's relatively low GHG. Whereas if you're getting it from China, it tends to be more coal-based, so higher GHGs. Cell production can vary significantly. We see some variance in the other cathode, and that's the cathode production processes. This is just sort of breaking this down, showing us the results on a GHG basis for the production utilizing the GREET baseline. The interesting thing here is that if we were to look at, for instance, the SOx emissions for this, what happens is the driver becomes nickel, right? Because nickel, it depends on where you're getting your nickel and how that nickel is being produced, right? So something like nickel from Russia, sulfidic ore, is going to be different than Canadian-based nickel from sulfidic ore, just because of practices of those locations. And then, as John was noting, if we're talking about laterite ore-based nickel, right, that's going to have a totally different profile. Sulfur's not going to be the issue, but there's going to be more energy required. So it's important to consider how these things are going to change with different battery chemistries. So that's the sort of thing that we're focused on. In summary, lithium and other material supply chains are critical in determining the LCA performance of these batteries. We are continuing to understand the material sources, the processing technologies utilized, so that we can better inform our LCAs. And of course, the lithium-ion battery market is dynamic, and I shouldn't even necessarily say a lithium-ion battery. I should say the battery market is dynamic, right? And so we have to ensure that we are staying abreast of what's going on in that market, increases in energy density, changes to cathode chemistry, anode chemistry, electrolytes, etc., processing technologies. So that's what I have for today, and thank you very much for your attention. Much thanks to the Department of Energy, the Vehicle Technologies Office for their support. Thanks.
Thanks, Jared. That was really interesting. So now looking a little bit deeper at lithium battery supply chains, I'd like to introduce Robert Pell. Robert is the founder and director of Minviro, a UK-based lifecycle assessment consultancy and technology company. Prior to starting Minviro, Robert completed a PhD at the Camborne School of Mines, and his research was focused on developing lifecycle assessment methodologies to quantify and mitigate the environmental impacts of technology metals throughout the iterative development stages and operations. Thanks, Rob.
Yeah, thanks very much. Okay, great. So it's a really interesting presentation so far, and I suppose we're at the point now where we're sort of focusing in on the raw materials that are going into these batteries and what that looks like from a life cycle assessment perspective. So, just in case nobody, I wasn't sure whether I was going to need this or if life cycle assessment was going to be introduced, but just in case there's anybody on the call that hasn't had that much exposure to life cycle assessment, you're basically capturing all the raw materials and energy inputs into a system, as well as the emissions, whether to land, air, and water. And you're referencing that against a functional unit, so a main product. So that might be, as Jared was mentioning, a spodumene product at a mine site, or it might be a refined product that's actually going into a battery. And also on this graph, we always highlight the co-products. That's a really important part within this life cycle assessment. So again, Jared was mentioning, a lithium brine process where you've got potash and lithium brine being processed with some shared processes. And so, allocating the environmental impacts is actually a really important part on this. So we always try and bring that up right at the beginning. Another point that we try and bring up is, you often hear the talk of scope 1, 2, 3 emissions. That seems to be used a lot in marketing and net zero commitments. So I think it's important to sort of identify how, although they're not life cycle assessment definitions, what life cycle assessment means in this context. And obviously the scope 1 emissions would refer to direct emissions. Scope 2 would be the embodied emissions from purchased electricity. And then scope 3, and when we talk about upstream scope 3, which is what is captured usually when we're doing life cycle assessments on products, this would refer to the embodied emissions of chemicals, reagents, consumables. And this is really, really important when we're talking about battery materials, because a lot of the processes can be chemically intensive. And so, yeah, this is important to capture. Okay, so Minviro recently published a white paper on the topic of life cycle assessment of an NMC 811 using the GREET model as a baseline for the actual model itself, but then looking at varying material impacts. So looking at if you source these nickel products, so nickel sulfate from different locations, if you source graphite, lithium, cobalt, manganese from different sources. And the reason we did this is because if you look at this figure, this is a qualitative figure, but it sort of, I suppose it mirrors what Gloria was mentioning very early on. Certain parts of the battery manufacturing are easier to decarbonize than others, and even parts of the EV total life cycle impact are easier to decarbonize than others. So if you're talking about the manufacturing, you can obviously improve processes or efficiencies in terms of dry room, for example. But one thing that is particularly challenging is decarbonizing the raw materials that are going to go into these batteries. And as John mentioned earlier, we're actually in a pretty challenging period in terms of providing enough of these materials for this significant transition. And is that going to mean that we're going to have to access some of these materials that might have different embodied impacts? So again, Jared mentioned sourcing nickel from laterite locations and maybe having energy intensive processes that are in regions that have coal dominant electricity grids. So, with all of this in mind, understanding that the raw materials is going to be a key component of making sure that the low carbon transition with EVs is done well, we thought we would publish this white paper just to highlight what it could mean. So as I mentioned, we use the GREET model, which, a fantastic tool for anybody that wants to test out, what an LCA of a battery looks like. We chose a high nickel content chemistry, so an NMC 811. And we chose this because we thought this would be interesting, especially with the trends in nickel sulfate production at the moment. You can see a very sort of simplified system boundary here on the right. And I suppose the thing that's important to keep in mind is everything in the model is static, apart from these inputs which you see in yellow. So we have 3 different production routes for nickel sulfate, 3 different production routes for cobalt sulfate, the same for manganese sulfate, the same for lithium hydroxide, and the same for anode grade graphite. And what I'm going to do is we'll go through some of the overall results, and then we'll dig into a bit of the detail after that as well for these particular material LCAs. So this was the high level result. So anybody can access this white paper and look at it in more detail. But basically, the high-level results were that low impact materials, as expected, much lower impact, with a cumulative impact of around 70 kilograms of CO2 per kilowatt hour. Bearing in mind that everything in the model is static and the manufacturing has been static, that's not the low impact production route for the manufacturing phase, but just for the raw materials. And then you've got commercial database values, and then you've got high impact materials. And you can see that the variance between the low impact and the high impact is really, really significant. And I think and you can see how, the cathode impact really jumps from just over 20 to over 60 from the low impact to the high impact scenario. And you can see also there's a significant jump in the anode impact as well, from the low impact to the high impact scenario. So we've sort of dug down into the actual contribution analysis for the cathode. And you can see this is the same order. So low impact is on the left, and high impact cathode is on the right. And as you would expect, so the high nickel content cathode is going to be sensitive to differences of impact of nickel production. So you can see that in the high impact scenario, it contributes to 54% of the total impact of the cathode, whereas it's a very meager, I think 12% in the low impact scenario. You can also see some other points of lithium hydroxide. It actually is categorized under other in the low impact, and then it's up to 9% in the high impact scenario. So let's dig down into some of the LCA results. These aren't necessarily underlying the calculations, but these are some commercially available data points. So you can see Terrafame, a European producer of nickel, they conducted an LCA recently and have a very competitive low impact to produce nickel sulfate, 1.8 kilograms of CO2 per kilogram. And then looking at some laterite project public data, and these are internal calculations, that can be around 11 kilograms per kilogram. And then the industry average nickel institute LCA there, that highlights the impact there. And again, lithium hydroxide production. So we actually published a white paper in early 2020, evaluating similar to what Jared mentioned earlier. So looking at the life cycle impact of producing lithium hydroxide from different sources. We looked at brines, both in Chile and Argentina, and then hard rock being produced in China, and then produced in Australia and then converted in China. The results are quite consistent. Great to see that Argonne were able to get primary data for the Chilean route. But again, this is really highlighting that depending on where you're sourcing materials, the impact can vary significantly. And it's really important that when we're doing LCAs for batteries, when we're doing product specific LCAs for batteries, it's important that we're getting the data right and not using just industry average values, because the conclusions can be completely different if you're just using industry average, because you can see the range is so big here. And so maybe one that I decided to focus on a little bit more detail is graphite. So graphite has often been not excluded, but a forgotten material in the battery when we're talking about LCA. That may be because there's a fair bit of opacity in the supply chain, especially getting Chinese data for some of the certain processes like graphitization. But we also published a white paper. This is also available. Feel free to contact me to get a copy of this, looking at the LCA impact of producing anode grade graphite from natural and synthetic sources. Now we know that a common anode is going to be a mixture, but we've kept the functional unit as just separate materials here, and it's a cradle-to-gate, so it's not actually looking at the sort of performance of the anode during the use phase. But you can see the processes here, different for natural versus synthetic. And you can see that although we're not giving the actual kilograms of CO2 per kilogram of product, the commercial databases that had graphite that were being used in these EV LCAs was significantly underestimating the impact. So the synthetic graphite production route was over 10 times higher than the baseline values that we used. And again, that's why we've seen in this case study that graphite is also a key sensitivity. And then I think talking about maybe going back to the how we can make sure that these raw materials for future batteries are going to be produced with the lowest impact possible. Myself with some other co-authors from different institutions, so British Geological Survey, University of Exeter, and GTK, we explored basically different deposit types for these technology materials for this low carbon transition, and evaluated what kind of methods can you use to make sure that we from now are planning to make sure that these materials are going to be extracted with the lowest impact possible. And although this is maybe a bit technical on the mining and engineering side of this talk, there's a proposal to integrate. This wasn't developed by us. There's some great work that's been done in this by people like Marcus Reuter historically, but integrating life cycle assessment with geometallurgy. So, are you able to? Can you make sure that you're making the best possible use of mineral materials in terms of energy and resource efficiency? And that's sort of integrating your mine planning with your processing, understanding what your mineralogy is, what your geology is. But this can also be linked with life cycle assessment. So, it might be that you can exclude a certain part of the deposit because it has a particularly high CO2 footprint, and you can go into a real high degree of resolution. So, this is some of the work that we've done, integrating that kind of thinking with life cycle assessment. What you're seeing here is a temporally explicit life cycle assessment. What is the impact per month or per quarter at a mine site producing this material, and how does it relate to other factors? Is it always to do with grade? Is it to do with penalty elements? Or and all this kind of information can help us get this material at a lower impact that can go into this low carbon transition. And then just maybe a bit of a plug in terms of how we're working with clients with this. We do this both through consultancy, but also technology solutions. So companies can use this sort of novel approach and modern thinking to try and minimize their impact of their products with a software, Mine LCA. And they can simulate ways to mitigate these impacts and hopefully in the future embed these into tools to be able to quantify the impact of batteries using these lower impact production routes. And then maybe just highlighting the team. So as you may have noticed from this presentation, our team really is filled with mining, mineral processing, chemical engineers. We do a lot of support with these, I suppose, upstream in the battery value chain to try and make sure these more raw materials are produced at the lowest impact possible. You can see we've got some sustainability managers analysts in the UK and then in the US as well, mostly working on lithium, and then some of the technical team as well. And just one more plug on, again, I think the same as Jared and many talks today, I've talked about climate change, but when we're talking about life cycle assessment, there's a whole broad range of impact categories, and it's important that they're not excluded when we're looking at a life cycle assessment context. So although we are focusing on reducing the climate change impacts a lot of the time, it's important that we capture other environmental impacts, exactly as Jared said, like acidification, if we're talking about different types of nickel deposits and processing routes. Thanks.
Thanks very much, Robert. Lots to consider there in terms of raw material supply chains. So I'd like to now introduce our next speaker. So I'd like to bring Dominic up. Thank you, Dominic. If you could share your slides. Dominic is a senior research analyst specialising in raw materials at Wood Mackenzie. He's responsible for developing sustainability and cost model analysis on current and future mining and refining operations. And he's going to be talking about ESG in the lithium sector.
Apologies for that, everyone. I'm having some technical problems, but I'll be with you momentarily. So apologies for that. So thanks, Gloria. So hi, everyone. Thanks for joining, and fantastic to see such a great turnout. So as Gloria said, my name is Dominic Wells. I'm a senior research analyst within Wood Mackenzie, and I focus on the battery metals sector. So it's great to be here today, and today we're going to talk about or discuss the effect of carbon tax schemes on the lithium sector. So obviously we've had some analysis going into detail on LCA and the NCM, well, the battery chemistry side of things, and I'm going to talk much more upstream and see exactly the financial effect that a lot of the carbon tax schemes are going to have on lithium producers and throughout the supply chain. So in this presentation, we'll look at how the cost bases of lithium producers are going to be impacted by carbon tax schemes as they're introduced, and how the effects of these are going to be felt from producer to producer, and by effect supply chain to supply chain, and where you're sourcing your material from, and exactly what measures we expect the lithium sector to make in response to these carbon tax schemes. So, taking a very quick review of the sustainability sphere. I'm surprised this diagram hasn't made its way into this webinar so far, but I'll be happily the first one to sort of go through it. So, as everyone knows, this is sort of quite ubiquitous in sort of society now. But ESG, environmental, social, and governance, the three sort of key pillars of sustainability, and how companies and supply chains are being regulated from to assess their impact on the world around them. So the environmental segment obviously looks at factors that are sort of centered around the conservation of the natural world. And within this, the big one for the mining industry is obviously carbon emissions, and the one that we're going to be looking at today. This is sort of given metal minings and refining, those sectors high energy intensities. More localized to this, of course, though, you have air and water pollution and water consumption. This is particularly important, in regions where water is scarce. And obviously, in addition to this, other important factors include the impact or effect of biodiversity, deforestation, and waste management. And it's this sort of E, specifically carbon emissions, that we're going to be looking at in this presentation today, but not to neglect the other aspects of ESG. So social, obviously relating to the consideration of people and relationships. This can take its form internally within a company. So illustrated by things like gender and diversity, employee engagement, and labour standards. And externally, more it's focused towards community relations and human rights, often sort of local communities. And finally, governance, which centres around the standards for running a company, and it focuses on things like board and executive gender representation and composition rates, bribery and corruption allegations, lobbying and political contributions, whistleblower screams, and sort of moreover a sort of general overview of the ethical leadership of any company. Now, these are obviously the main E, S, and G schemes, but this is by no means an exhaustive list. So when looking within the commodity space, we find great variation in the importance of ESG items between metals specifically. And here they're classified into three sort of sections, three silos, but in reality, they're often interlinked, and they span multiple sectors. Additionally, while some ESG factors can be measured, such as CO2 emissions, for others, it's very difficult to assign them a quantitative value. And how you assess the importance of one against another sort of quickly becomes a sort of a higher task, and can often lead you into hot water because it'd be relative to an individual's point of view. And what often sort of gets lost is sustainability is not just about being the best, not just having the lowest CO2 output. It's about embarking, on a journey of continual self-improvement to be the best company, mine, supply chain that you can be. However, with all that said, today we are focusing on lowering CO2 emissions and how emissions output of individual operations and supply chains are going to affect them from a cost-based perspective. So combining Wood Mackenzie's emissions benchmarking and emissions analysis with its cost benchmarking analysis as well. So something that was sort of hinted at by Jon earlier actually was an increasing number of players in the lithium sector have begun to react and respond to downward pressure from regulators and investors as the fulfillment of ESG metrics becomes almost as important as the fulfillment of financial metrics or financial performance itself. So looking at sort of this slide here, what we have is, from the investment and OEM side, we've seen initiatives such as the EU Battery Passport Scheme and Carbon Border Adjustment Mechanism sort of being brought into effect in the future. We see companies like Mercedes sort of only sourcing material from IRMA, the Initiative for Responsible Mining Assurance Assets, the ones that have been approved by that organization. Tesla and BMW have both committed to responsible sourcing initiatives of their own. And then we have, in a sort of similar vein to that, we have companies such as Panasonic and CATL both committing to net zero targets by 2030 for Panasonic and 2060 for CATL. And what this does is this then impacts mid supply chain players such as cathode manufacturers. In this case, you have BASF, LG Chem, and Sumitomo Corporation all committing to being carbon neutral by 2050, and Umicore net zero by 2035. And then this in turn impacts the upstream sector as lithium producers look to improve their GHG credentials. So looking at how these affect the upstream sector in the real world, you have SQM, for example, committing to net zero and reducing its water consumption. A very similar story at Albemarle, both Chilean-based brine producers, Atacama-based brine producers. You have Sigma Lithium Resources and Livent both issuing green bonds, so financial investment options based on their fulfillment of ESG metrics as well, sort of, organized by via third parties. You have Pilgrim Minerals investing in renewable energy technology with its solar farm, and also renewable energy based processing technology as well. Orocobre with its commitment to 20% renewable energy by 2030. And then more generally, you have spodumene refineries switching to natural gas as opposed to coal for the calcining stage. And then you have new lithium projects seeking to use more renewable power. So just on this slide, this is just some examples of initiatives being undertaken at various stages of the lithium supply chain, but was really sort of highlight how downstream OEMs and regulators drive improvement throughout the supply chain. So, an excellent example of that, it would be Mercedes saying that they will be looking to source via IRMA approved assets, and then you have SQM aligning themselves with the IRMA scheme. So how will the cost base of lithium producers be affected by carbon tax schemes? So to explain this graph shows the effect of 3 separate carbon tax prices on the lithium sector, specifically the 90th centile producers within the cash cost curve, both in the brine and mineral concentrate assets. So what does this show? So under these 3 carbon tax scenarios, which are each aligned to various global temperature targets, along with the $60 a ton, which is currently what the EU ETS carbon tax price is. So this graph examines the effect of carbon taxes on the highest cost producers in each respective segment right now, and therefore those are the kind of most exposed to cost fluctuations within their supply chain, or within their cost base. So in each of these scenarios described here, lithium production costs, including taxes levied from carbon taxation schemes on embedded CO2 emissions in their refined lithium, are expected to increase. And this is due to higher embedded emissions. Lithium chemicals produced via mineral sources are going to be subject to the highest taxation rates because of those higher embedded emissions within those within producing refined lithium from spodumene or hard rock sources. So, for example, under an EU ETS scheme with prices just hovering around $60 per ton, this would mean a 13% increase in the cash cost base of mineral concentrate producers within the 90th centile, compared to just 5% at brine producers on average. However, introducing $110 per ton and $150 per ton, which are 2 degree and 1.5 degree aligned global carbon prices respectively, you would expect to see at $110 per ton, you'd expect to see a 23% increase in cash cost base, and at 150, 31% increase in the cost base at mineral concentrate producers. This has already been said in this webinar already, both by Jared and Robert, but lithium produced via mineral concentrate sources is more emissions intense on average than that produced via brine. In fact, we estimate that it's about 3.5 times more emissions intense on average between the two sectors. So the key takeaway from this is that supply chains sourcing their material from mineral concentrate sources are significantly more exposed to carbon price fluctuations than those sourcing from brine. Though, of course, brine sources or brine producers have their own ESG concerns outside of carbon emissions, with concerns of water consumption, for example, though many producers are sort of taking steps to mitigate this in the sector right now. So this curve shows the overexposure of supply chains using mineral concentrate feedstocks to carbon price changes, even at a carbon price of just $60 per ton of LCE. So in this graph, this is 2025 total cash cost curve. What we have as brine and mineral integrated operations, and by mineral integrated I mean all the other mineral projects which use clay sedimentary deposits, perform much more favorably. And this is due to their generally lower cost bases and the lower carbon intensities of these operations in the first place, especially in the case of brine producers. So brine operations benefit from lower operating costs due to less active flow sheets and a restricted realization and selling costs, whereas clay mineral operations often benefit from quite significant byproduct credits on site. So while the previous slide examined the rising prices of the 90th centile of producers in both of these sectors, this graph shows that throughout the mineral concentrate sector, costs will increase relatively evenly throughout all centiles of the industry. And this is because while a correlation between cost and emissions intensity remains true when breaking out the industry by brine and mineral concentrate, the mineral concentrate sector will continue to be reliant on coal-dependent refining capacity, often predominantly situated in China, midway through the decade when this curve is set. So how will changes in expected emissions impact cost bases in the future? So in future, Wood Mackenzie expects emissions intensity in mineral concentrate supply chains to reduce as operations become more integrated and they make greater use of more efficient and renewable energy sources. The greatest driver of lower emissions is expected to be the replacement of coal-reliant calcining capacity, predominantly in China, as I sort of mentioned before, with natural gas-based capacity. So there are examples of this already happening in various Chinese refineries, though this is sort of likely down to more to local regulation aimed at reducing local particulate matter pollutants as opposed to any greenhouse gas related legislation. However, despite this, new refineries are by and large being constructed with natural gas as fuel for the calcining stage. Now, the calcining stage uses quite a significant amount of energy, which is just to say the sort of the breaking down of the spodumene concentrate, and it's the sort of primary step after a spodumene concentrate has been produced. And replacing coal with natural gas here and excluding all of other factors leads to approximately a 30% drop in the supply chain's emissions intensity just by replacing replacing coal with natural gas, in this specific stage. And then this reduction obviously has financial benefits as well. So in the scenarios presented on this slide, total cash costs for producing refined lithium from mineral concentrate will reduce as producers replace coal with natural gas in the calcining stage and develop this domestic refining capacity outside of China. And this reduces the embedded emissions from transport of mineral concentrates, a kind of handy byproduct as operations look to integrate. So as a result, the higher cost differential of producing lithium hydroxide in Australia will undo any benefits in the carbon tax cost improvements. So simply replacing coal with natural gas in China will lead to a 27% reduction in carbon tax costs, as China still relies heavily on coal for electricity, and the transport of large volumes of mineral concentrates is still required. However, continuing to develop Australian refining capacity such as Kemerton and Kwinana plants will lead to a 61% reduction in cost due to the reduced emissions from electricity. Australia has a much lower carbon grid than China on average, and this reduced transport however. However, as I sort of hinted at before, these come with elevated cost in other areas of the supply chain. So producing refined lithium in Australia and with natural gas is more expensive overall due to the production of higher cost lithium hydroxide, a higher cost of natural gas, and a higher operating cost outside of China. Though obviously the scenario that we're looking at right now is all under a scenario in which carbon costs are trade at $60 per ton. And as you can see from this graph as well, despite these improvements in the supply chain that we do expect to happen sort of over the next decade or so, brine, the carbon tax cost of brine producers on average is still going to remain lower. So thanks very much for listening. I hope this presentation's given a very good general overview of the risks or the risk exposure of the lithium sector to carbon price fluctuations, and absolutely happy to answer any questions either in chat or via email.
Thanks very much, Dominic. I think it's going to show the importance of life cycle analysis going forward and robust inventories. So finally, I'd like to now introduce Dr. Stuart Coles, who's going to be speaking about an outlook for EV batteries and their environmental impact from 2025 and beyond. Stuart is a reader of sustainable materials and manufacturing at WMG, University of Warwick. He leads work on life cycle analysis of lithium-ion batteries and has developed models for lithium battery manufacturing as part of Innovate UK funded projects such as MindBit. So over to you, Stuart.
Thank you for the introduction, Gloria, and thank you for all the talks as well that have come so far. My talk is really going to focus on what's coming ahead. There's been a lot of sort of talk about where we are and some of the pitfalls and problems that we've had to date. And I'm now going to sort of focus a little more about what's coming up in the future. I start off by sort of explaining the title of my talk, and it's to say why I've picked 2025 and beyond rather than any other particular date. And the main reason is actually something that Jon alluded to earlier, was that there is a draft regulation in place that's coming in from the European Union around sort of batteries and accumulators. And that's the kind of the updating of the existing regulation that currently sits within the EU, the UK, and anybody who wants to sell batteries. Now, the draft regulation was released a little under a year ago now, December 2020, and it's currently in the process of going through a variety of different stages before being finalised. The next point that is on the timeline at the moment is that one of the European Union's committees, the Committee for Environment, Public Health and Food Safety, are receiving a report from the rapporteur at some point in October 2021. So that report may have been received. I haven't been able to find any sort of public information around that, but there are updates going on, and as indicated, it's expected to be sort of finalised in and around 2022. So in this piece of regulation, there are 13 proposed measures which have varying levels of ambitions in each area, and some of them really have direct relevance to the future of LCA, how we conduct LCA, what sort of data we need, and some of the other issues that we've been speaking about so far today. Anyone who sells a battery within the EU will be required to meet these regulations, so it's going to be pretty much important for most OEMs, etc., to have an understanding of what's coming ahead. And the targets that are set within this regulation typically start around 2025 and are being phased in over the next 5 to 6 years. So that's why we're looking at kind of 2025. But the reality is that in order to meet some of these targets, the work kind of needs to start now, if it hasn't already started, and kind of ramp up some of the priorities in which we have. Now, one of the measures is around carbon footprint. Now, that obviously links to LCA quite heavily. And the minimum expectation of this particular regulation is that there will be a carbon footprint declaration of a battery, some point estimated around 2024 and 2025. So if you want to put a battery onto the market, it's going to have some kind of carbon footprint declaration. Then come somewhere between 2027 and 2030, there's likely to be a maximum threshold for batteries as a condition for placement onto the market. Now, this is very similar to the emissions regulations, where automotive manufacturers have had a fleet average for their carbon emissions. So currently 95 grams of carbon dioxide per kilometre. We're likely to see some kind of maximum threshold for batteries in a similar vein. But the problem with these statements is almost what they don't say, and there will be a dedicated impact assessment. But as we've already discussed, there is a large degree of variation in materials, a large degree of variation in manufacturing processes, in locations, in supply chains. So when they say a carbon footprint of a battery, there is no specific as to what that carbon footprint of that battery might be. And so what would we included in an assessment? And I think that's probably one of the biggest challenges that we're going to face over the next few years, is deciding what should be included in the scope and how it's being calculated. You know, the literature is, there's a great raft of some really good research out there on lithium-ion batteries and various battery chemistries and looking at the life cycle assessment, but inevitably there's a big variation in terms of their scope, inventory lists, and so on. So how do we come to a decision of what we're going to compare? And I think that's probably the biggest area of work that is required. If you break it down into broadly 3 phases that we've kind of been touching upon, we'll have a manufacturing phase, a use phase, and a recycling phase. Now, which ones of those would be included in a carbon footprint of a battery? Certainly the manufacturing stage, it would almost have to be included. We'd need to have that as part of it. But then do we include the use phase? It would almost be disingenuous to not include it, because other transportation methods will have their use phase emissions that they'll be measured on. And if you don't include it, you're almost stoking the fires for maybe some of the internal combustion engine enthusiasts who would like to promote the fact that, you know, ICEs are better, and they will point to the fact that the carbon footprint of manufacturing a battery is higher than manufacturing an internal combustion engine by the design, the materials, the complexities, and so on. And with that, so we need to ensure that the right data is coming forward to ensure that those comparisons can be made fairly, that actually the reduction in use phase emissions is actually quite substantial, and therefore we get to a final product, a better overall assessment, but lower carbon emissions, etc. Equally, when is recycling included into these calculations as well? What data is available, and so on? And that's probably, arguably, our biggest problem right now in terms of where we sit. We've seen already today that there are some pockets of data that are around, but we are struggling to get the true volume of data. Where does it all sit? What are we looking at? Where are the materials coming from? And so having the data to back up the life cycle assessments that we are now having to carry out, and rather than previously, you know, people like ourselves on this call and people who are interested are thinking we should do LCA, we should look at the environmental footprint. It was should, and it was deemed to be the right sort of thing. Now we've moved into a phase where it is going to be mandated. We're going to have to do it, and it needs to be supported with data. But that data also needs to be consistent again across multiple different partners, supply chains, etc. And so if we look at manufacturing, we've already identified that there's gaps existing, particularly surrounding some of the technology metals. We've spoken a lot about the metals involved in the batteries, but also around the motors as well, some of the rare earth materials in there. There's quite a few gaps, and the data is coming along, and there's certainly projects around that are moving forward to fill those gaps in, but that data needs to be added in. We've seen very eloquently put that location, scale, and technology have huge impacts on the overall carbon impact of a lithium-ion battery. And again, this needs to be quantified and standardized as part of these sorts of assessments. And really a big question I sort of think of at these points, how transparent are these supply chains in order to be able to make these assessments? How do we know where our materials are coming from? Now, there's no, you know, traceability within this sector is a subject, and people are looking into it. But, you know, the implementation of technology such as blockchain might give us some kind of extra help as to where materials are coming from, but there needs to be a level of transparency so that we're clear on where materials are coming from to enable us to complete these assessments correctly, because the conclusions will be very different depending on where you're sourcing many of these materials. And moving a step further, as we start to develop some of the technologies moving from 2030 to 2035 and beyond, some of the emerging ones like solid state batteries, we have very little understanding of what the manufacturing might look like, what the composition of materials might look like. There's an idea on lab scale. There's some again really good research, but what about scaling up and moving into that sort of more industrial production? And that's somewhere where there needs to be more of a focus of LCA as a forward-facing tool, looking at it from a perspective going into the future, to give us not only an idea of what the carbon footprint will be, but also where the optimization can occur. What are the hotspots? Where are the problems that we should be looking at? Because this needs to be done in conjunction with the development of the technologies rather than retrospectively, because it's a lot harder to make these changes retrospectively rather than using it as part of that design process. We've also got the use phase. We know that there's zero emission at point of use in terms of electric vehicles, and this is all being driven by the current legislation to reduce exhaust emissions. But the energy generation has related carbon emissions, and this is something that is, as I've mentioned before, this is often sort of thrown back as like, well, you've still got to generate electricity. But you know, the models that we've done at Warwick have shown quite clearly that unless your battery vehicle is a very low mileage car, sort of the type of kit car that you might take out on a Sunday afternoon for a bit of a spin in good weather, but the rest of the week it sits in the garage untouched. Unless it's those sorts of low mileage vehicles, batteries are the clear winner in terms of carbon footprint. So that in the use phase and where it sits has to be included in these calculations. But if it is to be included, how is it going to be calculated? Is it going to be done via a projection? Are we going to look at what we think the carbon footprint of the national grid and other grids around Europe, China, America will look like in the future? Or are you doing it based on a flat line on the point of sale? How is that comparison going to be done? Again, in order to make sure that it is fair, robust, and can ensure consumers have a good choice of an understanding of what they're buying. We also have to look at end of life and some of the issues and discussions around recycling. And again, recycling has come up today. But really with recycling, the impact here from a life cycle assessment perspective is that lack of data. How do these processes stack up? And we've seen there are some tools emerging that will do these calculations. But how does that sit moving forward? What's the impact of using recycled materials in a battery again? How does that impact the manufacturing of the material? Because that ultimately then impacts the carbon footprint and that statement that you're required. So if you're going to include recycled materials in your battery, which, as we'll come to in a minute, is going to be mandated, we need to know what the environmental footprint of those processes are, because it's going to need to be included as part of a manufacturing assessment. So we also need to be developing life cycle assessment of the recycling sector as well. And there are processes being developed, but it needs to sort of move on at a pace to kind of make sure that we're ready in 2024, 25 for these sort of full battery life cycle assessment statements. And that brings us on to the recycled content. We are going to have some kind of mandatory declaration of recycled content, probably from 2025, maybe a little bit later, stating exactly how much recycled content is in a battery. And it's likely that there will be mandatory levels of recycled content from 2025, 2030 and then 2035, two varying different levels. And they're going to have mandatory targets for the recycled content of lithium, cobalt, nickel and lead in batteries on those two targets. So the reason that they're putting that in is really, it's more of a economic tool that we're now having a predictable framework that will enable investment, because they know come 2030 there will be a market for about 10% inclusion, 20% inclusion of lithium and cobalt. The targets are available online as to what the market will be demanding at that point, and that will enable the investment in the recycling technologies to take off. But again, as that investment comes in, there needs to be the LCA development alongside, because it needs to feed in to the carbon footprint of the overall battery manufacturing. Another thing that is coming on and will need to be shared, and this is an interesting one about transparency in supply chains, is that there will need to be the measure called provision of information, and all batteries will need to have printed and online information available that effectively is going to help people shift towards more environmentally sound batteries. The idea being that now everyone's going to have to say everything about their battery in terms of the environmental footprint. And there will be a kind of battery passport, some kind of QR code that will enable second life operators and recyclers to potentially improve efficiencies. But the information as to what is in that battery passport still seems to be a little bit vague, and particularly around battery condition, what's the state of health of the battery, are things that are going to need to be really important here. And the reason why it's important is because it helps that decision making as to what should happen next. You know, if that state of health is particularly good, could it be used to power some robotics in a factory, or could it be used as secondary life energy storage? Now, a lot of repurposing of batteries, people are very reticent to do that because of safety concerns. The batteries haven't been designed for those applications. There are some real issues in incorporating them into those technologies. We don't know how well or badly treated that lithium-ion battery might have been as part of the car. So understanding a little bit more about what that battery passport is going to do, again, is going to enable some of the decision making. So things like LCA to feed into maybe multi-criteria decision analysis that enables depiction of what route should go where. You know, this battery has a state of health of 65%. It's made up of an 811 chemistry that determines that actually it should go straight to recycling. We don't want to use it for a second life. Those kind of decision-making tools are going to be fundamentally based on environmental and economic decisions. So that information needs to be able to be freely available as well, and is planned to be as part of this provision of information. The final part that is kind of also touches upon LCA, but in a slightly different way, is that everyone is going to be required to do some due diligence on their supply chain, and that requires people to address social and environmental risks related to raw material extraction, processing and trading. So some of the materials that are sourced from areas which are a little bit more unstable, that have some kind of societal pressures, that's going to need to be incorporated in. And so not only are we looking at environmental life cycle assessment, but also social life cycle assessment, an area that probably doesn't get as much coverage as it should do in certainly within this space. I can wholeheartedly agree with Rob's comment earlier about making sure that we're thinking more than just carbon emissions, and I think it extends even further, that we should be looking at some of the societal impacts as well as the environmental ones. They are much harder to quantify and deal with, but they are equally as important. This is going to be impacted by some of the EU's other work on sustainable corporate governance. There was a roadmap that feedback is closing this month, and that's going to impact exactly what the sort of due diligence is going to look like and what measures are going to be put in place as part of this proposed measure. So really, the conclusion is that LCA is going to be hugely important, because we're now going to move away from a part where we should be doing it to somewhere where we have to do it. It's now inevitable. You go, OEMs, people are going to need statements of what the battery manufacturing is, and that is going to drive people to reduce it. As soon as you set targets and you put metrics in place, people try and get lower. You use it as a competitive tool within the marketplace. With recycled content also being mandated, we need to know more about how it impacts on the recycling process, how the environmental impacts can be fed into manufacturing, how can we lower the global warming potential and other environmental impacts by using recycled material in the manufacturing supply chain for batteries. And it's quite likely that we're going to need to have some kind of discussion as to what the scope of a battery assessment looks like. How are we going to make it fair and comparative for everyone, so that we've got it's a system that we can believe in and trust in, and that's likely to involve, or a full sort of cradle to grave assessment for the carbon footprint of a battery. I'd like to thank you all for listening, and much like everyone else, welcome questions.
Thanks, Stuart. Some really big methodological questions there that we have to answer, and there's lots of those in the chat. We've now come to 3:30, which is kind of like the end of the webinar, and it's been a fantastic afternoon, some really interesting presentations. If there are some questions, we would like to potentially pick them up with the speakers afterwards, so we'll get back in contact with you. So just again to thank John, Gerard, Robert, Dominic and Stuart for their presentations. Just to say that Zemo Partnership will be running some further webinars. We're going to be running another one in December and hopefully in January as well. And if you go to our website, you've got a lot more information there about the work that we're doing and when our webinars will be taking place. So thanks again, everybody, and I hope you found this afternoon interesting. Bye-bye.